Okay, so just like we have a public static dome train task run, let's implement public static dome train task delay that allows the user to pass in a time span to specify how long they want the delay to last. This is actually a pretty easy method that uses some tricks under the hood. So the way this is going to work is we'll queue up a new dome train task, or rather we'll initialize a new dome train task. And that is the task we'll be returning. But before we return, we're going to take advantage of the timer in .NET. And the way timer works, it allows us to pass in a callback. So this callback is where we're going to say task.setResult, essentially completing the task. And whatever is waiting for the method delay to finish will then be allowed to proceed and move forward. And we'll use the change method on our timer here to specify how long that delay is. And lucky for us, actually not coincidentally at all, the change method allows us to pass in a time span. So let's just pass in the time span delay that the user gave us. And then the other thing it allows us to do is specify a period. So if we want this timer to repeat, we could have this timer repeat every 5 seconds if we wanted to. But as we see in the IntelliSense here, it says you could just specify an infinite time span to disable that periodic signaling. So to prevent our timer from running forever, we'll say timeout.infinite time span here. So this is telling the timer to only run once, to specifically run with this delay that the user has given us for dome train task.delay. And when it does run, all it's going to do is say task.setResult, which, if you remember, we wrote down here, and it just completes the task. So it looks to see if there's an exception or if there's any continue with, it'll run all that for us. But let's jump back to our program and see where we can add this in. So this is the same code we wrote last time. Let's just run it and see how quickly it finishes. So it almost runs immediately. So let's go ahead and add in a delay here. So let's say dome train task.delay. And let's tell time span from, how about 1 second? So let's add in a second delay here. And then let's add in a 1 second delay here as well. So we'll run this code again, and we'll likely see different background thread IDs. That's okay. But the difference we're looking for is we should see a pause in between when these items are printed to the console. So let's run it, and nothing happened. Well, that was actually my fault, because yes, we're calling .delay, but we're not waiting for it to finish. So thread 1 kicked off the delay on a background thread and then immediately moved on. So let's make sure we also say delay.wait, and let's run it again. There we go. So there's a second delay. There's another 1 second delay, and that looks really good. That's exactly what we expected. Now, the only thing that's kind of ugly about this code is we have this kind of a dangling modifier here. We have this .wait, and this is the only way that we're able to tell the dome train task to wait until what it's calling finishes. So in other words, this is the only way for us to tell thread 1 to not continue on until this background task is finished running. Now, this isn't terrible. This code works, this code executes, but let's think about what's going on here is that thread 1 is kicking off this background thread, and meanwhile, thread 1 is sitting here waiting. So thread 1 is locked, and that's one of the reasons .wait is dangerous. When we call .wait on our tasks, not just our custom dome train task, but if we say task.run and then we say .wait, well, we're going to lock the calling thread. In this case, thread 1 is calling dome train task.run. Thread 1 is the calling thread that gets locked by .wait. So what we'd rather do is replace .wait with the await keyword, because not only does this code read much more easily because it's left to right, top to bottom, instead of looking for these dangling .wait modifiers at the end of each line. When we read the code, we see the await keyword, and we know that this dome train task.run will complete before it moves to the next line of code. And likewise, we know that this DOM train task.delay will complete before we move to the next line of code, but we're getting all these red squiggles. So let's jump back into our custom DOM train task and implement the code necessary for this await keyword to work with DOM train task. So the last thing we're going to do with our custom DOM train task is to make it compatible with async await in C#. And the way we're going to do that is to first create a new struct. So let's create a public read-only struct, and let's call it a DOM train task awaiter that implements iNotify completion. Now, if we think about how async await works, the await keyword essentially tells .NET to run that task, and then when it's done, pick up back where it left off. But how does .NET know when that task has completed? Well, this is where our DOM train task awaiter comes in. So let's create an internal constructor that kind of mirrors how .NET works, because .NET has their own task awaiter under the hood, which we cannot initialize as developers because it's only meant for internal use only. So ours will mirror that here, even though we're the only ones using this program. But for DOM train task awaiter, it's going to take in a DOM train task, and we're going to assign that to be a read-only DOM train task, and we'll just name the field task. Done. Now we're getting yelled at because we haven't implemented iNotify completion yet. So let's tell JetBrains to implement that for us. For onCompleted, this is the method that's going to run once our DOM train task awaiter has completed. And maybe you could already guess, we're going to call task.continuewith and tell it to continue on this continuation action. Now, the task awaiter in .NET also has a couple properties we'll add in here. So that is public bool is completed. And you'll see a theme that all of these essentially reference the task. And what else? We're going to add in public DOM train task awaiter get awaiter. We'll just return this. And we'll say public void get result, which will return task.wait. Now, back in our DOM train task, we're going to add in one more method. We're going to add in public DOM train task awaiter get awaiter. We're going to tell it to initialize a new DOM train task awaiter, passing in the current task. And believe it or not, this is the magic method that if we jump back to our program, all of a sudden, there's no more red squiggles. So let's show these side by side because this really is crazy. This is .NET using something called duck typing. Let's say I remove this method. So I comment out the getAwaiter method from my DOM train task, and all of a sudden, the await keyword says that this is not awaitable. Re-implement this method, and those red squiggles go away. This is because .NET uses a concept called duck typing for async await. Async await doesn't actually look for a specific interface or a specific base class. All async await looks for is, does your code have a method called getAwaiter? And let's see what happens if I comment out iNotify completion. Now we also see async await is invalid because even though we have a method called getAwaiter, it returns a DOM train task awaiter that doesn't implement iNotify completion. So what .NET looks for to make sure something is awaitable, to make sure we can use the await keyword with it, is that it has a method called getAwaiter, and then that method returns a type that implements iNotify completion. So again, this is called duck typing in C#, where our code here on the left isn't looking for a specific interface or a base class to acknowledge the implementation. It's actually looking at the shape of our class to see, does this class have a specific method called getAwaiter that returns a type implementing iNotifyCompletion? If so, great, then we can use the await keyword. And this comes from the old saying that if it looks like a duck and it quacks like a duck, it's probably a duck. Essentially insinuating that we don't have to do, say, a DNA test to see if this animal is a duck, because we can make some assumptions on how it looks and how it sounds and how it behaves. And that's where we get the concept of duck typing, which in this case, the await keyword is looking for our getAwaiter method. So let's come back now that we've implemented async await and see how this code runs. And look at that. Our code starts out running on thread 1, just like we expect. We run DOM-train task.run, but we await it, meaning we're waiting for this line of code to finish before running the next line of code, which is where we had our 1-second pause, which I saw those as the console write lines were rolling in. Now, the only difference here is that this second DOM-train task ID was also run on thread 5. But the only thing that's different is that we did not return to the calling thread. We didn't return back to thread 1 before continuing on and running this line of code on line 11, where we print the second DOM-train task ID. Now, this is because console apps don't have a synchronization context, which is what .NET uses to allow us to return to the calling thread after we hit the await keyword. So like we saw in the previous course, usually we hit the await keyword, the calling thread returns, in this case, thread 1 returns. And if this is a UI app, the thread 1 is able to interact with the user. The thread 1 is able to redraw the UI if the user starts scrolling or clicking buttons. But in this case, this is a console app, and console apps don't really have a UI, which is why they also don't have a synchronization context. And without a synchronization context, we cannot return to the calling thread. Now, if none of that makes sense, that's okay, because we haven't explained what a synchronization context is, but we will. So check out the last course in this lecture where we dive deeper into the synchronization context to really understand what's going on here. And I'll see you then.